Welcome to the physics class for December the 2nd. I have looked over the test results, but I have not had a chance to look over the partial credit work that you submitted. I did notice that about 2/3 of you submitted some work in hopes of getting partial credit, so that was very encouraging. In previous tests, a lot of you guys just blew off the partial credit and it really hurt you. So it looks like you've learned your lesson there. So I haven't had time to go through all that. That's going to take me quite a while. So don't be surprised if your final test grades don't show up on Aspire until this weekend. Probably expected probably Sunday evening is when it usually works out for me. Okay, but the raw scores that I looked at prior to partial credit are not that bad. I mean, in some cases, yeah, not so good, but for the most part, they're not that bad. And so if you get a little bit of partial credit, I think your scores are going to be up to where most of you are going to be pleased with your test results. Not all of you, though. Okay, so let's see, a few other announcements I should make before we get into the new material. First off, tutoring is ongoing. There's tutoring every Tuesday and Thursday at 4 o'clock from 4 until 5. And there's also tutoring every Friday during the day, starting from 11:30 and going for about an hour. So it's really important that you take advantage of the tutoring sessions. If you don't use them, you will lose them. Principal Wilson is not going to continue them if people don't show up for the tutoring. So definitely show up. So that means this coming Thursday, 4 o'clock, there will be tutoring, and Friday at 11:30, and then next Tuesday. Okay, another thing, you might think that there's a lot of time left before the term ends, but don't forget there's a 2-week Christmas break or holiday break, winter holiday break. So that actually there isn't very much time left before this term ends. Now would be a good time to start thinking about extra credit if you want to do it, especially if you're planning on making a video rather than just answering the questions for the videos that have already been posted. If you want to make your own video, you get more credit for doing that than you do for answering questions. And that's not something that can be done in a weekend. So get started on it now. I've had a few people send me requests, ideas for videos that you want to make, and I'm very glad to see that. Please do communicate with me before you make a video, not afterwards, because I've seen so many times where people make a video and I look at it and I say, yeah. But if they had talked to me beforehand and I had been able to suggest, make a little change here, a little change there, then their video could have been a really good video. Okay, so do that. And also, if you want to just answer the questions that are in the video, that's fine too. You don't get as much extra credit for doing that as you do for making a video, but still, do it for a couple different videos. You can max out your extra credit that way. So don't delay on that. All right, well, I think that's it for all the administrative details. Let's go ahead and start into the new material. Let me just share my screen really briefly here. Okay, so notice that what you see on your screen right now is chapter 9, not chapter 8. We are going to have to skip chapter 8. If we did everything in the book, there's no way that we would be able to get it all done by the time that the school year ends, even if it wasn't for coronavirus. Even back in the good old days when we met in a classroom, still, there's just not enough time to do all the cool things that are in the book. So chapter 8, it causes me great pain to skip it because I think there's really good stuff in there that you need to know, but you got to skip something. So we are going to skip chapter 8. So we're going to jump right straight into chapter 9, which talks about momentum. You will find that when you read the chapter before you do the homework, because I know you always read the chapter before you do the homework, right? There are a few things in the chapter here where they're going to make references to stuff from chapter 8, and it's not going to make sense because we skipped chapter 8. So I will tell you what those parts are. And I will tell you it's okay to just, skip this part here. Most of the stuff that's in chapter 9 is stuff that you'll have no trouble with, and that is the only stuff that we will do. Okay, so let me just stop the share there. Okay, so let me ask you about a couple words that I trust that you have heard many times in your life. And you may have even used these words, but do you really know what the words mean? Okay, so the first word that I want to ask about is the word momentum. Momentum is a word that I'm sure that you guys have heard in your lives at some point. Momentum. Can anybody here tell me, what does the word momentum mean? And maybe give us an example of using it in a sentence. Nobody wants to jump on that one? Nobody knows what the word momentum means? I find that hard to believe.
I feel like it's similar to motion, but that's all I know.
Okay. Definitely motion is an important part of it. Okay. How about in the political terms? You sometimes will hear on the news, so remember back at the presidential elections, I don't know if you guys paid much attention to them, but early on, if you looked at the Democratic contenders, Bernie Sanders was somebody that they said he had a lot of momentum because he was a candidate in the previous elections 4 years ago. He already had a lot of followers. He already had a lot of support. And so going into the election this time around, if you look at the news, you probably heard people talk about the fact that Bernie Sanders he already has a lot of momentum just right at the very beginning. In fact, some people said that he had more momentum than Joe Biden did. But then as the election year went on, Joe Biden, he gained momentum, and Bernie Sanders tended to lose momentum. Okay, so that's a word that they talk about in the news a lot. And so I see Lily has typed something in here. She says, doesn't it have something to do with speed? Like if you're skiing and there's a hill and you have to build up momentum to go up the hill. Yes, you're exactly right.
Wouldn't it have to do with, like, I guess you could say, like, gaining like potential energy or something, perhaps, to
Yeah.
keep going?
There is a connection between momentum and energy, very definitely. So energy is the next thing that we're going to talk about. After we learn about momentum in chapter 9, we will then move on to other chapters where we talk about energy. So they're certainly related. I like what Lily said about, let's say that you're skiing, and so you're coming down a hill, and there's a flat part up ahead. So you see there's a flat part. And you know that if you don't get a lot of momentum going, then when you come to that flat part, you might not make it all the way through, and then you're going to have to walk through the flat part. So that's not good. So what you do is while you're still on the slanted part, you want to build up a whole lot of momentum so that you can make it through the flat part without stopping. That is a great way to think about it. Luke, did you say something? Sounded like you did.
It should be just kinetic energy, I think, or something
Okay.
related to it. It is related to velocity, but it's also related to mass, like Cora just put in the chat there. Because, like, if I roll a marble down a ramp, it's going to have less momentum than a bowling ball.
Okay, yeah, what you are saying is absolutely true. What Cora typed into the chat box here saying, isn't a product of mass times velocity? Yes, that is exactly right. So when we talk about a politician having momentum, that's just figurative. If we want the literal definition of momentum, it is exactly what Cora just typed into the chat box. And let me open up a whiteboard here so that I can actually write it on the screen. So momentum is defined as, so I'm going to put 3 lines here. Okay, so an equal sign with an extra line above. Now that line on top should not be a squiggly line. That line on the top should be a flat horizontal line. Okay, so this is a symbol that I have used before, and I'm going to use it again many, many times. So the 3 horizontal lines means is defined as the mass of an object multiplied by the velocity of that object. So in words, you could think of it as momentum is kind of inertia in motion. So previously we talked about inertia, and we said that the more mass you have, the more inertia you have. So that means if the more mass you have, the harder it is to start you moving. But once you are moving, the more mass you have, the harder it is to stop you from moving. Okay, so mass is basically a measure of your inertia. Okay. But momentum is more than just inertia by itself. It's inertia times the velocity. So that if you have a really massive object, so let's suppose you have a great big freight train. It's got 100 cars all filled with some, coal or whatever, but it's just sitting there on the tracks. It's not moving. So it has tremendous inertia because it's got a lot of mass. But if it's not moving, then it doesn't have momentum. Okay, so momentum is inertia in motion. One way to think of it is the more momentum that you have, the harder it is to stop you. Okay, so that train, if that train is moving, it's got so darn much mass that it's going to be very hard to stop that train. And the faster it moves, the harder it's going to be to stop. So you can see that it makes sense that it's mass times velocity, not just mass by itself. So that is what momentum is. All right, so words are hard to write. I prefer to have 1-letter abbreviations. So for mass, well, that's just M. Velocity, that's just times V, okay? And so I need a 1-letter abbreviation for momentum. So I could call it M, but that's clearly not going to work because I've already got M. M stands for mass. So if I try to use the letter M for momentum, that's just going to get confusing as all get out. So I better pick a different letter. The letter that scientists use for it is the letter P, which at first glance might be very puzzling and say, why in the world would they use the letter P for momentum? Well, in the Latin language, the word for momentum in Latin starts with the letter P. So that's where they get it from. Okay, so when we do equations we're involving momentum, we're going to use the letter P to stand for momentum. So momentum is mass times velocity. All right, so we're going to do a bunch of problems in your homework where they say, how much mass does this object have? So pretty simple, just what is the mass of the object multiplied by what is the velocity, and that'll be your answer. Now, you guys know the velocity is a vector, so I'm going to put a little arrow above the V there, just to remind us that velocity is a vector. Now, mass is not a vector. Because if someone says, what is the mass of this calculator? And you say, well, it's about 0.2 kilograms to the north. That makes no sense. Okay. A mass doesn't have direction to it. So mass is a scalar, but velocity is a vector. Okay. So if you have a scalar times a vector, that means the answer is going to be a vector. So momentum is also a vector. So I'm gonna put a little arrow above it just to remind me that it's a vector. So if I were to ask you, what is the momentum of this car that's driving down the road, and you say, well, the mass of the car, let's suppose the mass of the car is 1,000 kilograms, and the velocity of the car is 25 meters per second to the east. Okay. So if I ask you what's the momentum of that car, and you say, well, the momentum of the car is 25,000, whatever units it is we use to measure momentum in, and you stop there, you have not completely answered the question, because momentum is a vector. So you would have to say that it's 25,000, whatever units it is we use to measure momentum in, to the east. Okay. So now the question then becomes, well, what units do we use to measure momentum in? Well, what units do we use to measure mass in? Kilograms. What units do we use to measure velocity in? Well, meters per second. So the unit there for momentum would be 25,000 kilogram meters per second, which is a pretty awkward unit. And quite often what happens is when physicists or when scientists in general, whenever they define a new term like momentum, and they say, okay, well, what are the units? And they say, well, the units work out to be kilogram meters per second. And they say, well, boy, that's a mouthful. We really ought to give it a new name. Let's call it something like maybe 25,000 Hendrixes or 25,000 Blurks or, whatever. That's the way they normally do it. But for whatever reason, which to be honest, I don't understand, they never did that for momentum. They never came up with a special name for the momentum unit. They just left it as kilogram meters per second, which is a little awkward, but hey, that's what they done. So, okay. So then the answer, in a homework question tonight, if they ask you, what is the momentum of a car that's got 1,000 kilograms of mass and moving at 25 meters per second to the east? The answer is 25,000 kilogram meters per second to the east. Just leave it at that. So those homework problems, the first couple homework problems are going to be really, really easy. Okay, now there is another term that it's a word that I'm sure you guys have used many times in your life. And you're going to find that this term is going to be used in your homework tonight, but probably in a different context than what you're used to hearing it. Okay, so this other word is impulse. Impulse. What does the word impulse mean? Anybody? I'm sure you've used that word before in your daily life. Like maybe you walked into a store and you went to the store to buy some milk. But as you're standing there in the checkout counter, okay, very good. Yeah, so Malcolm just typed in the chat box. He said it's like an urge. So yeah, if you do something on impulse, it's something that was a sudden urge that you had, not really something that you planned to do, but you just got this sudden urge. So the example that I started to say there was that you went to the store to buy some milk. You're standing in the checkout counter, waiting to pay for it, but there's somebody in front of you, so you got to wait for them. So what do you see in front of you as you're waiting to check out at the store? You see a rack full of candy bars or other types of things that are what they call impulse buys. These are things that you didn't go to the store to buy the candy bar, but you sit there waiting to check out, you see the candy bar, you get a sudden urge to buy the candy bar, and so you buy it. So people in the marketing business, they have a word for that. They call it an impulse buy. So you bought it because of this urge that you had, okay? So that's what the word impulse means for people who are not physicists. Now, when you read the homework, when you read the book tonight before you do the homework, you're going to find that we use the word impulse, but we use it in a totally unrelated, completely different meaning. So in physics, the word impulse is defined as the amount of force that you exert on some object multiplied by the time that force is acting on the object. Okay. All right. So force, well, that's just F. Time, I could call it T, but don't be surprised if sometimes you will see it written as delta T, where remember delta, anything means the final minus initial. So delta T means T final minus T initial. Okay. Now, most of the time when we do problems like this, we start our clock at the time when the force begins to act on the object. So T initial is usually always 0. And so that means that delta T then is the same as T final. So a lot of times they just leave out the delta. So sometimes you're going to find that impulse is equal to force times time, and other times you're going to see it written as force times delta time. It's the same thing. Okay, so I need a one-letter abbreviation for impulse. So you might think, well, let's use the letter I for it. Now, there are some textbooks that do use the letter I for impulse. There are other textbooks that use the letter J for impulse. So let me just say J or I. And a lot of times people, they just write out the word impulse. But okay, so for me, I will probably use the letter J more often than I use the letter I. But I'm going to try to mix it up just because I want you guys to get in the habit of seeing it both ways. Because when you go on to later physics courses, I want you to not be surprised if some books call it I and other books call it J. Don't worry about it. It's the same thing. Okay, so let's leave it as I for right now. So let's say that I equals F times T. Okay, so I'm going to leave it. I'm going to get rid of the J right now. Okay, so I'm going to leave it as I equals F times T. Now, F is a vector. T is a scalar. So whenever you have a vector times a scalar, that means the answer is going to be a vector. So that means impulse is also a vector. Okay, so again, in your homework tonight, they're gonna start off with some really simple questions where they're going to say, okay, I've got some force where the magnitude of the force is, oh, I don't know, let's say maybe it's 12 newtons. And the amount of time that this force is acting on some object is, oh, I don't know, let's say that it's 4 seconds. Okay, and so they're going to say, how much impulse did you give to this object? That's the way they're going to word it. Okay, well, impulse is force times time, so that's going to be 12 times 4. So you're going to say the impulse then is 48, whatever units that we use to measure impulse in. But again, if that's where you stop, then you have not fully answered the question because impulse is a vector. Okay, so now in this case, you would say, well, the reason I didn't answer the question was because you didn't fully specify it. You told me the magnitude of the force, but you didn't tell me the direction of the force. Okay, so what we really should do then is we should say that the force is 12 newtons to the west. Okay, so then the final answer would be that our impulse is going to be 48, whatever units we use to measure impulse in, to the west. Okay, so now that brings up the question, well, what units do we use to measure impulse? And so I'm going to approach this the same way that I did with momentum. Okay, what are the units we use to measure force in? Well, that's newtons. Okay, what units do we use to measure time in? Well, that's seconds. Okay, so then clearly the units for impulse are going to be newtons times seconds, or Newton seconds. Okay, and if we wanted to, we could give this a name. We could call it 48 Wilsons, or 48 whatevers. But again, for whatever reason, the scientists who set this up, they never decided to give it a special name. They just left it as Newton seconds. And so that will be the answer. So the impulse that we give this object is 48 Newton seconds of impulse. Okay. Now, sometimes the force that you exert on some object is going to change as a function of time. So let's suppose that I'm going to graph force as a function of time. Okay. And so let's assume that the force is constant. Okay, so let's say that I start pushing on some object, and I push on it with a force of, what did we say last time? Did we say 12? I think we said 12, right? Okay, good. Okay, let's go back. So let's say that the force is 12 newtons. And the amount of time that we did it was for 2 seconds. So here's 0, here's 1, here's 2. Okay, so at the end of that 2 seconds, we stopped. So the force then dropped down to 0. Okay, so if impulse is defined as force times time, and now I'm just going to talk about the magnitude of the impulse right now. Okay, well, the force, that's 12, the time, that's 2. So what you see here is that the area of this curve here works out to be the impulse. Now, so what if the force is not constant? Let's suppose that I have a spring. I should have grabbed the spring. I don't have any springs handy. Imagine I've got a spring, okay? And I squeeze the spring. Well, you guys have played with springs. You know how springs work. At first, it's really easy to squeeze, but the more I squeeze it, the harder it becomes to squeeze. So let's say I've got this spring. In fact, let me close this so you can see it a little better here. So I've got a spring. Boy, I wish I had it. Okay, well, I don't. Okay, so pretend that this is a spring. Okay, so I'm gonna squeeze it, and the more I squeeze it, the harder it gets to squeeze. So at first it's easy, then it gets a little harder, and then a little harder, then a lot harder. Okay, so now I've got this compressed spring. So I'm gonna take this compressed spring here, and I'm going to take some object like my calculator, and I'm going to put this compressed spring right here, and maybe I have a wall right here. So tell you what, let's go back here to our whiteboard. Let's draw a picture, because you're going to have things like this in the homework today. So let's suppose that I have a floor here and the wall, and here is my compressed spring, and here is some mass that's sitting here. And so I let go of it. So initially I'm holding the thing, I'm stopping the thing from moving, but then I take my hand away. So what's going to happen to this object? Well, if I do a free body diagram, the spring, oops, I hate it when I do that. I was still in erase mode, not draw mode. Okay, so the spring is pushing on this object. And so if I were to make a graph over here on the left, showing the force on this object as a function of time, at first, when the spring is compressed, there's a lot of force. As the spring relaxes, and because the thing starts moving, when the spring is not compressed as much, the force on it is less than it was before. And we're going to study a lot about springs later, but what you're going to find is it's a linear relationship. Okay, so what's going to happen is you're going to have a lot of force at first, but then as the time goes on, the force gets less and less and less. So if I want to calculate the impulse, how can I calculate the impulse if the force is changing? Okay, so if the force is constant, then I just use I equals Ft, no problem. If the force is changing, how can I do I equals F times T if F is not a constant? Well, those of you who are in calculus, you know that there is a way that you can do this, because that's what calculus is all about, is working with things when those things are changing. Now, it's not my intention to teach you calculus right now, but what I'm going to do is I'm going to say, well, look, but what was the case up here when the force was not changing? Okay, when we said I equals F times T, when the force was constant, it worked out to be the area underneath the curve. So if I graph force as a function of time, that's what the graph of force function over time looks like. But if I look at the area under the curve, the area equals the impulse. So I'm going to tell you now without proving it, I'm just going to state this, that it works the same way when the force is changing. That the impulse is equal to the area under the curve. Now it has to be a force versus time curve. It can't be a force versus distance curve. It has to be a force distance time curve. So the impulse works out to be the area under the curve. Okay. And so this is something that calculus students do all the time. And calculus students have a special symbol that means area under the curve. It's this squiggly symbol that looks like that. Okay. And they have a word for it. They call it the integral. Okay. So the area under the curve is called the integral. And now we have to tell which curve it is. So we have to say that it's the curve of f as a function of time. And the way that a calculus student says as a function of is they put a little d there. So I equals integral of f dt is the way that they would say it. Okay. And so I see Caleb is talking about sigma. So sigma and integrals are very closely related. I don't want to spend time talking about the difference right now. I'll let your math teacher talk about that. And Luke is telling me that I forgot the bounds. Okay, so it's the integral from starting when t equals 0 and ending when t equals whatever number that I want, which in this case is 2. Okay, all right, but so I don't expect you guys to know calculus, but I do expect you to know that this symbol right here, that elongated S symbol, means area under the curve. Okay, I do expect you to know that. So in your homework tonight, they're going to ask you questions where they're going to give you something like I just did. Like they're going to say, okay, let's suppose that we graph the force as a function of time and there's 0 force for a while, but then all of a sudden there's an increasing force and then it stays constant for a while and then it decreases. And they're going to say, what was the impulse? And usually they're just interested in the magnitude of the impulse. So I would write it this way, where they might just write it this way. They will say, what is the magnitude of the total impulse that was delivered? And you're going to say, well, how in the world am I going to calculate that if the force was changing? Well, just break it up in little pieces. Okay. So we've got a rectangle. You guys know how to calculate the area of a rectangle. We've got a triangle. You guys know how to calculate the area of a triangle. We got another triangle. You guys know how to calculate the area of that. So you don't need to know calculus in order to answer this question. Just because all of the questions they're going to give you in the homework tonight are going to be really simple ones. Now, if I had a weird thing like this, so if I had f as a function of t and I had a curve that looked like that, okay, well, then you're going to need calculus for that. Okay, but they're not going to give you any like that in your homework tonight. They're all going to be simple ones where you know how to calculate the area. Okay. All right. Now, something else you're going to need to know for tonight's homework. Okay. They're going to tell you something like, let's suppose that I have some object that is sitting on the floor, minding its own business, not bothering anybody. And I come along and I push on this object with a force of, I don't know, let's say that it's 21 newtons. And let's say that I push on this object for a time that is, I don't know, let's say that it's 4 seconds. Okay. And I want to know how fast the object is going to be moving afterwards. Okay. So I want to know, so if V initial equals 0, I want to know what is V final. Now, in this case, they're going to need to give you a little more information. They're going to need to tell you what the mass of the object is. So let's say the mass of the object is 6 kilograms. and we're going to assume that there's no friction. Okay, this is a problem that you could solve. You could solve this using the equations of motion, the equations that I like to call the Dr. Seuss equations. You could do this, okay? You know that F equals ma, and you know what F is and you know what m is, so you can calculate what A is. So A equals F over m, okay? So you get some number. I'm not going to take the time to get it now, but you get some number. And then you say, okay, now I need one of those equations of motion, one of those Dr. Seuss equations. And you say, well, if I'm looking for VF and I know what A is, probably the best equation to use would be VF equals V naught plus AT, because V naught is 0. So I didn't know what A was at the very beginning, but thanks to the work I did over here, now I know what A is. And they told me what T is, and so bingo, so I can figure VF equals some number. I can get it, okay? Well, it turns out that if you know a little bit about momentum and impulse, turns out there's an easier, quicker way to do it. There is a very useful thing called the impulse momentum theorem. So impulse momentum theorem. Okay. The impulse momentum theorem says that however much impulse you give to something, that equals the change. Let me do that a little better. The change in momentum of the object. So this is something that they state in the book. And in fact, they then prove it. But for right now, let's just make sure we know how to use it, and then we'll learn about how to prove it. So impulse, I'm going to use the letter I for impulse, even though a lot of textbooks, they prefer to use J for it, okay? Equals change, well, that's delta. Momentum, well, that's P. So that tells me that the impulse is equal to delta P, okay? So if I've got that object that was sitting there not minding its own business, and I wanted to know what was the final velocity, well, what I could do is I could take the impulse momentum theorem and I could replace I with F times T. I could replace delta P with delta, wait, let me do that again. I could change delta P with P final minus P initial, which is the same thing as M times V final minus M times V initial. Now, in the example that we just did, V initial was 0, so I can get rid of that. Okay, so then what I can get then is the V final equals F times T divided by M. And I'll get the same answer that I got before, but I get it in a way that's a lot easier and quicker. Okay, so this impulse momentum theorem that you see right here is going to make your homework problems tonight a whole lot easier. So just remember that the impulse is equal to the change in momentum. Now, do not make the mistake of thinking that the impulse is defined as the change in momentum. I see a lot of students, they make that mistake. They think that impulse is defined as change in momentum. And to that, I say no. I mean, it is true that impulse is equal to the momentum. So this statement right here, where I've got an equal sign here, that is a true statement. But this statement right here, where I've got a is defined as statement, okay, that's not true. Impulse is not defined as delta P. Impulse is defined as the force multiplied by the time. Okay.
So could you use this to solve problems where the mass is changing?
Aha, yes. Yes, you could. And in the U of U physics class, you might. Sometimes he does it, sometimes he doesn't. It depends on how much time they have. But yes, so if you have, like, for instance, you get into relativity where, you know, I don't want to get into it right now, but later in the year, we're going to talk about special relativity and general relativity. And you're going to find out that the mass of an object actually does change. And so this is a great way to deal with that. But let's not get into that right now. Okay, so in your homework tonight, you're going to find that the impulse momentum theorem will allow you to solve problems a lot quicker and a lot more easily than you could solve them using the Dr. Seuss equations the way that we've been doing it up until now. So it's a good thing to know. Okay. Now, hopefully you guys have learned that, to me, a very important part of physics is not just taking some equation and using some equation that we don't know where it came from. We need to know where the equation comes from. That is something that I find to be very, very important. That's what makes physics physics. Where do the equations come from? So I'm sure you can guess what I'm going to do right now. We are going to derive the impulse momentum theorem. And it's very possible that when we take our next test, deriving the impulse momentum theorem might be a question on the test. Now, some of you might groan and you say, oh no, those derivations, they're so long. I got good news for you. This derivation is incredibly quick and simple. This is the easiest derivation we've done all year. Okay, so I would recommend that you get out a new or turn to a new page in your notebook. And up at the top of the page, I want you to write derivation of impulse momentum theorem. Okay. And make sure that you know how to do this. Okay, so I'm going to start with something that hopefully everybody agrees is true. I'm going to start with Newton's second law, F equals ma. Now, some of you are going to say, well, shouldn't you put a sigma in front of that F? Well, I'm only dealing with one force. I'm assuming that we've got some object sitting here on the ground, not minding or not bothering anybody, and we're pushing on that, and we only have one force at work here, so I don't need the sigma. Okay, so F equals ma. Motion in one direction, yes. Okay. Okay, so what is A? Well, you know that A is defined as the change in velocity divided by the change in time. That's a definition that everybody hopefully agrees on. So that means that F then is equal to mass times delta V divided by delta T. Okay, so hopefully everybody says, yep, no surprises there. All right, what am I going to do now? I'm going to multiply both sides by delta T. Okay, so that cancels that. All right, what am I left with? F delta T equals M delta V. Okay, but what is delta V? Well, that's just V final minus V initial. So this is M times V final minus V initial. Oops, try that again. Okay, all right. So if I now distribute the M out, what I get is M times V final minus M times V initial. Okay, so that is what F delta T is equal to. And then I look at that and I say, well, hey, well, that's just P final. And this, well, hey, that's just P initial. So what have I got? I've got P final minus P initial. So that leaves me with F delta T equals delta P, which is the impulse momentum theorem. Okay, so that was pretty quick and easy. All right, so now we know that we can trust the impulse momentum theorem. It's not just some equation that some guy somewhere claims is true, but we don't know whether or not to believe him. Okay, now we know that it is in fact true. We can use the impulse momentum theorem. Okay. Any questions about what I've covered here? Okay, now there is one more thing that I need to tell you in order to help you with tonight's homework. And once I finish with this one thing, then we'll be done. So there is one important law of physics that you need to know. And this law is called conservation of momentum. what that means is that as long as there's no outside force acting on an object or a group of objects, okay, the total momentum that these objects have at the beginning of whatever event you're interested in has to be the same as the total momentum after this event that you're interested in has occurred. Okay. Now, the event that we're generally going to be most interested in tonight's homework is collisions. So let's suppose that I have some object that's floating through outer space, and it has a mass with, let's call it M1, and is moving with a velocity that we're going to call V1. Okay, and I'm going to put a little arrow above the V just to remind myself that it's a vector here. All right, and then we've got some other object, and let's say it's a bigger object, although it doesn't have to be bigger, just some other object. It has a mass of M2, okay, and it's moving with some velocity that we're going to call V2, okay, and so it could be moving to the right or it could be moving to the left. Doesn't matter. Let's assume that it's moving to the left. And so let's say here, so this is V2, okay? And so now these are in outer space, so we don't have any forces acting on them, you know, like gravity or anything else. They're just floating through space. And so this is the before picture. All right. Now let's suppose these guys crash into each other and they stick together. Okay, so my after picture is going to look like this. And so here is the one blob. Here is the other bloblet. So these are blobs of clay. Okay, so when they hit, they stick together. Okay, I want to know what direction are they going to be moving and how fast they're going to be moving. So in other words, what I want to know is what is V final. Because remember, these are vectors. Okay, so I want to know what is the magnitude of the velocity after the collision, and I also want to know what is the direction. So hopefully you guys see that if the velocities were the same, but the M2 was bigger, then that means after the crash, the two of them are going to be moving to the left. But that's not necessarily going to be the case, because even though the mass M2 is bigger, if it turns out that the velocity of V1 was way bigger than the magnitude of the velocity of V2, it is possible that the final velocity might in fact end up moving to the left or to the right. So it's not obvious at the very beginning which direction I should choose. Okay, so what I'm going to do then is I'm going to just say, well, I'm going to arbitrarily choose that my plus direction is to the right. And I'm going to draw my final velocity as if it's pointing to the right, even though I know that might be wrong. And then I'm going to do the math. And when I come up with a number for my V final, if the number that I get is negative, then I know that it's actually going to the left and not to the right. So I don't have to worry about it. Okay, so now I need some sort of an equation that I can use in order to solve this problem. The equation that I'm going to use is the equation for conservation of momentum. So I'm going to write it the way that a mathematician writes. I'm going to say if I add up all of the momentum before the crash occurred, okay, so this sigma here, well, you've seen that many times before in this class. We've talked about sigma F. That means we've added up all the forces. So in this case, we're going to do the same thing. We're going to say sigma P means we're going to add up all of the forces before the crash occurred. And the law of conservation of momentum says that that has to be the same as what I would get if I add up all of the momentum after the crash. Boy, I just cannot write today. Okay, so all of the momentum before the crash, if I add it all up, has to equal all of the momentum after the crash if I add it up. And this is if and only if there are no outside forces acting on these guys, like for instance, gravity. Okay, and so that will be the case. All right, so now I have an equation that will allow me to solve this this problem. All right, so let me see, where can I get some space to do this? How about, let's clear a little space up here at the top. Okay, so my conservation of the momentum equation says, if I add up all the momentum before, okay, so that means m1 times v1 plus m2 times v2, that is going to be all of my momentum before the crash. Now notice, I didn't say v1 with an arrow above it, or v2 with an arrow above it. I said v1 without an arrow and v2 without an arrow. So I'm going to trust that you guys understand that what I mean then is the magnitude here. Okay. But to be completely correct, what I really should do is I really should put the arrow above to remind myself that the conservation of momentum here is talking about vectors. Okay, so that has to be equal to m final, which if the two of them are stuck together, so the total mass is going to be m1 plus m2 together in parentheses times v final. Okay, and let me put an arrow above there, just to remind me that it's a vector. Okay, so it's time to put some numbers on here. So let's suppose that the M1 is 1 kilogram and M2 is 2 kilograms. Let's say that V1 is 10 meters per second to the right. So that means it's a positive 10. Let's suppose that V2 is 3 meters per second to the left. So that means that the magnitude of V2 is going to be a negative 3. Do not forget the negatives. Okay, so then what I can do then is I can say, so I do in fact need to work with magnitudes here. So I'm going to get rid of these arrows here because I need to work with the magnitudes of them. So what I'm going to get then is that 1 times a positive 10 plus m2, which is 2, times its velocity, and the magnitude of it is negative. So negative 3, okay? That has to equal the sum of the two of them together, which is going to be 3 times v final. Okay, so from this point on, it's no longer a physics problem. Now it's just a math problem, and you're good at math, right? So what have I got? I get 10 minus 6. So that gives me 4. So I get 4 equals 3 times v final. And that means v final then is 4/3. And notice v final is a positive 4/3, not a negative 4/3. So that means that my guess here turned out, the way I drew the arrow, I drew it in the positive direction. So, and I get a positive number for v final. So that means it is in fact going to be moving to the right. So even though M2 is more massive than M1, M1 was moving so much faster that it had so much more momentum that after the collision, the mangled mass of the two of them together is still going to be moving to the right, okay? And it's going to be moving at a speed of 4/3 meters per second, okay? So this equation here, conservation of momentum, this is the key to solving your problem, sir. Okay, so Teague is saying it would be 4. Are you saying I made a mistake here, Teague? Because I've certainly made lots of mistakes in my life. Oh, okay, you're saying never mind. Okay, good. Had me worried there. I was afraid I would have to wear the wig or something.
So
Good.
how would you factor in like gravity into this? Because is gravity considered like an outside force? Like even just between the two masses?
In this case, yes, gravity would be considered an outside force, and that would mess things up big time. I don't want to take the time to go into it right now. I think I've hit you with a fire hose of new information right now. I don't want to go confusing it. So let's hold your question until next time we meet, if you don't mind.
All right.
So yeah, remember that the conservation of momentum only applies if there are no outside forces. Gravity does count as an outside force. Okay. Now, if we have blocks sliding along a frictionless floor, so even though gravity is acting on the blocks, that gravity is going to be balanced by the normal force of the floor. So if we have blocks sliding across frictionless floors, which I think you probably will in your homework tonight, don't worry about the fact that gravity is there. As long as it's canceled out by the normal force, we're fine. We can ignore it. But if it's not canceled out by the normal force, then yeah, then that messes things up. Okay, well, we still have 20 minutes left in class, but I think it's best that we stop right now. I don't want to give you any more new stuff. I think you're going to be overwhelmed if I do that. So let me just tell you what the homework assignment is, which I really don't need to do because you guys can look on. One thing I do need to tell you is I do need to tell you what parts to skip. That's important. Okay, so let me share my screen with you right here. Okay. Okay. So here's the homework assignment for tonight. I want you to read the first part of chapter 9, but make a note of this. This is important. You're going to find that at the bottom of page 233, they start talking about something called angular momentum. So everything that we have done up until now is called linear momentum. I didn't use the term linear momentum because I didn't want to confuse things. So when you have things that are moving in straight lines, the momentum that you're talking about is linear momentum. But if we had studied chapter 8, you would know that you also really need to worry about an object rotational motion as well. Like for instance, this is a picture that you're going to see in the book where they have a diver who is jumping, and you can see here that the diver is following this path here, this parabolic path, that's basically projectile motion, which you guys know how to do that. But here's the interesting thing. You can see that the diver's body is rotating at the same time that it's moving linearly. It's also rotating, okay? So if you want to fully understand the situation, what's going on, you need to not only account for the motion of the diver's center of mass, but you also need to account for the fact that the diver is rotating, okay? But in order to do that, you would have had to have studied chapter 8, which we did not do. So what I'm telling you now is that when you get to the bottom of page 233 and they start talking about angular momentum, you can skip that. So all the way from the bottom of page 243 until the bottom of page 235, you can skip all of that. And the homework problems that I've assigned will only talk about the type of momentum that you guys understand. I've purposely left out any problems that talk about angular momentum, so you don't have to worry about those. Okay. Okay. Charisma is saying that I haven't posted the assignment yet on Canvas. I didn't? I thought I did. Maybe I forgot to hit the publish button. I do that sometimes. Okay, well, it's a good thing I told you here what it is. All right, so make a note of it. Here it is. And then as soon as I end this meeting, I'll go post it on Canvas. Okay, thank you for telling me about that, Charisma. Okay, are there any questions? Okay, remember, class is not over. We still have almost 20 minutes left. Use the time to read the chapter. Don't just start into the problems, guys. You need to get in the habit of reading the chapter before you do it. There's a problem in the chapter that I think is really good. In fact, problem number 1 is a really good example. Problem number 1. I mean, okay, this is a really good problem. Read through the book. I'm not going to take the time to do it. It's not my job to read the book to you. You guys need to read the book yourself. Make sure that you spend a lot of time looking at example problem number 1 and see how they did it and see why they did it that way. It will be very, very helpful. Okay. All right. Well, if you have no questions, you go ahead and type bye into the chat box, and I'll see you later. If you do have a question and you didn't want to ask it because you knew it was being recorded, here I will stop the recording, and then you can ask your question without embarrassment.